In section 7.3, we're looking at simplifying radical expressions. It is possible to simplify some radicals that do not evaluate two rational numbers. To do so, we use a product rule and a quotient rule for radicals. The product rule states that if the nth root of a and the nth root of b are real numbers, then I can just smush them under one nth root as the nth root of ab. So let's go ahead and look at example number 1. We want to multiply the fourth root of 5y squared times the fourth root of 2x cubed. So we're just going to put this underneath 1/4 root and then multiply. So we have 5y squared times 2x cubed. And then we're just going to simplify a little bit. This becomes the fourth root. 5 times 2 is going to give me 10. We have x cubed and y squared. Let's go ahead and take a look at another one. We have the square root of 2 over a times the square root of b over 3. So we're going to put this all underneath one big old square root, and then we're going to multiply. We have 2 over a times b over 3. And remember, when we multiply with fractions, we multiply across the top and bottom. And so on the top we have 2b, and on the bottom we have 3a. And that can't be simplified anymore, so we just go ahead and leave it as is. We also have the quotient rule, and it looks very similar to the product rule where we smushed it underneath one radical. We can do the same thing with division. So if I have the nth root of a and the nth root of b, as long as the nth root of b is not 0, then I can pull a division apart as two separate radicals, as the nth root of a over the nth root of b. So let's go ahead and take a look at example number 2. We have the square root of x over n, and so we're just going to make a square root on the top. Square root of x over a square root on the bottom, square root of 9 on the bottom, and so we end up with the square root of x all over 3. Let's go ahead and try another one. We have the fourth root of 3 over 16y to the fourth. So same idea, we're going to split this into two separate fourth roots. And so we have the fourth root of 3 all over the fourth root of 16y to the fourth. I can't simplify the numerator, but I can simplify the denominator. So we end up with the fourth root of 3 on top, and on the bottom we end up with just 2y. Now we can use both the product and quotient rules to simplify a radical, but I personally like using factor trees because you don't have to be super comfortable with your perfect squares or perfect triplets or even our perfect fourths to simplify with the product and the quotient rule. So let's go ahead and take a look at the square root of 50. So what I'm going to do is I'm going to break 50 down into its prime factors. It doesn't matter what factors you use because once you're done simplifying everything, you will get the same answer. So I'm going to break down 50 into 5 and 10, and 5 is prime, but we can break down 10 as 5 and 2. And so because we're looking at a square root, the index is 2, and that tells me how many numbers need to look the same to group them together. So because the index is 2, we're looking for pairs of numbers that look the same. And so I have a pair of 5s that I can pull out as a single term, and then I have a 2 that's left over. So make sure you're only looking at the bottom of our branches of our factor tree. And so the square root of 50 can be simplified. Whatever we circle comes out as a single number, so just as a single 5. And then anything that I underlined in purple is going to stay underneath the root. And so this simplifies as 5 times the square root of 2. Let's look at the cube root of 24. Again, we want to break down 24 with our factor tree. We have 4 and 6, and then 4 and 6 can both be broken down. 4 is 2 and 2, and 6 is 2 and 3. So because the index is 3 this time, we're looking for triplets of the same number. So we have a triplet of 2's, and then we have 1 3 left over. So the cube root of 24, we pull out the 2, and then underneath the cube root, we still have a 3 left over. And so when I simplify this, we end up with 2 times the cube root of 3. Let's look at 26. Well, 26 is 2 and 13. Well, we don't have any pairs of numbers that we can pull out, so we can just leave them underneath. And whatever we have that's left underneath, we just multiply together. The same thing happens on the outside. If I pull out more than one number, we just multiply them together. And so actually the square root of 26, since we're just going to multiply the 2 and the 13 together, we end up just getting the square root of 26 is already as simplified as it gets. Let's try a 4th root. We have the 4th root of 32. So 32 is 4 and 8, and 4 can be broken down into 2 and 2, and 8 is 2 and 4, and then again our 4 can be broken down into 2 and 2. So because the index is a 4, we're looking for 4 of the same number. And so we actually have 4 2's, and we have 1 2 left over. And so we pull out our circled 2's as just 1 2, and then underneath the 4th root, we still have a single 2 left over. And so we end up with 2 times the 4th root of 2. In general, we say that a radicand of the form the nth root of a is simplified when the radicand a contains no factors that are perfect nth powers, other than 1 or -1. So let's go ahead and use the product rule to simplify something a little bit more complicated. We're going to start adding some letters in here, but it's going to work very similar to when we just had numbers. So the first thing we're going to do is we are going to split these and look at the numbers and the variables separately. So the square root of 25x cubed, we have the square root of 25, and then we have the square root of x cubed. Well, 25 is a perfect square, and so we can simplify that easily, but let me show you how it works with the factor tree. So when I break down 25, we get 5 and 5 as our answer. And so again, my index is 2, so I have my pair of 5s I can pull out, but I have nothing left over, which means that it's a perfect square. So when I simplify, I just have a 5, and my square root goes away for the square root of 25. But when I'm talking about x cubed, remember this just means it's x times x times x. So again, we're looking for pairs of the same thing. So I have a pair of x's right there, and I have one x left over. So one x is going to come out, and then underneath our square root, we're still going to have one x left over. And so what we get as a final answer, everything in pink is what was pulled out of the square root, so it's going to stay on the outside. We have 5x, and then everything in purple is what stayed underneath the square root, which is just a x. And so our final answer is 5x times the square root of x. Let's go ahead and look at something a little bit more complicated. We have the cube root of 54x to the 6, y to the 8th. So let's go ahead and split these up. We have the cube root of 54. We have the cube root of x to the 6. And we have the cube root of y to the 8th. Let's look at 54 first and break this down. 54 can be broken down as 6 and 9, and 6 can be broken down as 2 and 3, and 9 is 3 and 3. So my index here is 3, so we're looking for triplets of the same number, and so we have triplets of 3, and we have a 2 left over. So we're going to pull out a 3, and then underneath our cube root, we still have a 2. Now let's go ahead and look at x, the cube root of x to the 6. So again, x to the 6 is 6 x's. And we're looking for triplets of the same thing. So we have a triplet of x's, and then we actually have another triplet of x's with nothing left over. So we have x times x, or we'll rewrite it as x squared, and then nothing left under a cube root, and then we have y to the 8th, and that just means that we have 8 y's. So triplets of the same thing, we have 3 y's, we have 3 y's, and then we have 2 y's that are left over. So we have a y and a y that were pulled out, and then underneath our cube root, we have a y and a y left over. So when I simplify this, everything in the pink is on the outside. We have a 3, we have 2 x's, or x squared, and we have 2 y's, or y squared. And then underneath our cube root, everything in purple stays there. We have a 2, and we have 2 y's, so y squared. So my final answer is 3x squared y squared times the cube root 2y squared. Now let's go ahead and use the quotient rule to simplify the following. We have the square root of 50x over 2 times root 2. So let's go ahead and just simplify the square root of 50x first. So we have the square root of 50 times the square root of x. And so we're going to break down 50 first. 50 is 2 and 25. And then 25 is 5 and 5. Our index is 2, so we're looking for pairs. We have a pair of 5s, and we're going to have a 2 left over. And with the x, we don't have anything we can pull out, so the x is going to stay underneath as well. And so end up getting 5 times the square root of 2x. So let's go ahead and rewrite the top. We have 5 times the square root of 2x divided by 2 root 2, which can't be simplified anymore. But what we can do is we can split that top into 2 separate radicals so that we can get rid of the square root of 2's. So we have 5 times the square root of 2 times the square root of x all over 2 times the square root of 2. And so the square root of 2's are going to cancel. And we end up with 5/2 times the square root of x. Let's go ahead and try another one. We have 7 times the cube root of 48x to the 4th y to the 8th over the cube root of 6y squared. So the first thing I'm going to do is I am going to combine this into one cube root so that I can simplify the inside a little bit. Our 7 is going to stay on the outside, but inside my cube root I'm going to have a fraction that I can simplify. I have 48x to the 4th y to the 8th over 6y squared. So let's go ahead and simplify. We have 48 over 6, which is 8. We have x to the 4th over no x's, so we're just going to rewrite x to the 4th. And then we have y to the 8th over y squared, which just gives me y to the 6th because we subtract the exponents. Now this is a lot easier to simplify. So let's go ahead and just split our cube root. So we have the cube root of 8. We have the cube root of x to the 4th. And then we have the cube root of y to the 6th. So looking at 8, that's 2 and 4, and 4 is 2 and 2. And so we were looking for triplets. And so it turns out that 8 is a perfect cube. Let's go ahead and do the x's and y's while we're looking at it. We have x times x times x times x. And so we have a triplet of x's. And we have one x left over. And then we have our y's. And so again, we're looking for triplets. We have 3 y's and 3 y's. So remember, everything in pink just gets pulled to the outside. So we have 7 times. From 8, we found out it was a perfect cube, and it was 2. With our x's, we had 1 x pulled out, and then we had 1 x left over. And then for y's, we actually pulled out 2 y's perfectly. And so what we end up getting as a final answer, we have 7 times 2, which is going to give me 14. We have an x on the outside and 2 y's, so y squared. and then we have a cube root of x. So we end up with 14xy squared times the cube root of x. And so the last thing we want to talk about is the distance and midpoint formula. The Cartesian coordinate system helps us visualize a distance between points. To find the distance between 2 points, we can use the following formula. If our 2 points are x1, y1, and x2, y2, we can find it by using d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. So let's go ahead and use this formula for the points 2, -5, and 1, -4. And then we're going to give the exact distance and then a 3 decimal point approximation. So I just like to label mine in order. So 2, -5 is x1, y1, and 1, -4 is x2, y2, but it doesn't matter which one is x1, y1, and which one's x2, y2. So plugging into my formula, I have the square root of x2, which is 1, minus x1, which is 2, squared, plus y2, which is -4, minus y1, which is -5, squared. And so we actually have a double negative that we can fix a little bit. And so let's just go ahead and simplify. Underneath the radical first, we have 1 minus -2, which is -1 squared, plus we have -4 plus 5, which is 1 squared. And so let's simplify a little bit more. -1 squared is 1, and 1 squared is 1. And so we end up with the square root of 2 as our exact answer, and the 3-point decimal approximation is about 1.414. The midpoint of a line segment is just the point that's located exactly halfway between two endpoints. So distance is going to give you a number. Midpoint is going to give you a coordinate. And so the formula for the midpoint, if my endpoints are x1, y1, and x2, y2, then we have x1 plus x2 over 2, and then y1 plus y2 over 2. All we're doing is we're finding the average of our x's and the average of our y's to find the average of our two endpoints, our midpoint. So again, I'm just going to label mine in order, but it does not matter. So P is going to be x1, y1, and Q is going to be x2, y2. And so using the formula, we have x1 plus x2, so -3 plus 1 divided by 2. And then looking at our y's, we take the average. We have 3 plus 0 over 2. And this is a coordinate. And then we just need to simplify. Well, -3 plus 1 is -2. And 3 plus 0 is 3 over 2. And so we can actually simplify our x-coordinate a little bit. That's going to give me -1, comma, and then we'll just leave the 3 over 2 as 3/2. And so the midpoint between my two endpoints is -1, 3/2.